I am recording. I just wanted to give you some information about the Unit 3 exam. In case you haven't had a chance to check yet, I sent you all an email to let you know that exam has been regraded based on any work you uploaded to the Unit 3 exam work assignment in Canvas. The overall grades on the exam were good. The average grade was a 78. The median grade, which is the middle one, is an 83, which is great. That means half the class scored at or above an 83 on the exam. If you scored less than that after the exam was regraded, you might want to rethink how you're studying for exams in this course. We have just pretty much one more exam left, and that's the final. Okay, the best way to study for these exams are to go over the practice exam that I provide. And usually the last online class session before the exam will have a recording of us going over the problems in that exam. Okay, for these unit exams, there was also a practice exam, and I noticed not everybody tried that. I have gone and given everyone full points for that assignment, whether you tried it or not. But again, this is a great way to practice for the exams. If you take the exam cold, it's going to be difficult to do some of the questions. Okay, so I just wanted to let you know those exams are graded. And what I did was, if you go into the Unit 3 exam assignment in Canvas, you'll see that I uploaded a print of your exam, and that will show you all the correct answers as well as any comments that I made, like explaining how to do a problem that you might have had trouble with. Okay, so take a look at those and let me know if you have any questions on either the exam or my comments, okay? So what we're going to be doing from now until the end of the course is we're going to be starting a new unit. So bye-bye probability and statistics, or at least until you see them again in GBS 221. Okay, what we're going to be talking about for the next week or so is going to be functions of multiple variables. Okay, so what is that? You're used to, so far, seeing functions where there's one input, the thing you typically call X, okay, and there's one output, the thing you typically call f of x or y, okay? So functions of more than one variable are exactly what they sound like. They have multiple inputs, okay? So you could have two inputs to a function, call them x and y, and call the output f of x, y, or z, okay? So again, there'll be a little bit of rearranging variables here, okay? But the thing to be comfortable with is function notation, right? If you see notation that says f of x in parentheses, you know there's only one input. If you see f of x comma y, you know there are more than one input. There are two, in fact. So what kinds of things can be modeled by functions of multiple variables? Oh, geez, lots of things. Okay, the first thing that comes to my mind is a joint cost function. Okay, where you may have two products, and basically the cost of producing the two products is a function of things specific to each of the products. So you've got two inputs. Other things that are used in economics are things called Cobb-Douglas production functions, and we'll take a quick look at some of those today, and they have multiple inputs. There's things that depend on, say, capital and labor as inputs, right? So you would have two inputs to a function there. So again, a lot of this stuff is used in modeling in economics and in finance, okay? But as business majors, you should at least be comfortable with the notation and what these things are telling you. So today we're just going to start off slow, and we're going to talk about functions of multiple variables and some of their uses. And then where we're headed with this topic is we're going to show you how to take derivatives of these functions, but with respect to each of the input variables. So it'll be a very basic review of derivatives. And then, of course, what we're going to use those for is finding maxima and minima of these functions of multiple variables, okay? So Here's the calculus in the course. This is pretty much why Math 213 came before this course. All right, but don't worry, we'll review the calculus before you need to use it for anything. And it's just derivatives. There's no integration or any strange stuff. Okay, so this should be pretty straightforward. Okay, so let me begin. And as always, if you've got questions, just unmute and ask or type them in the chat. I'll keep the chat open as we go along. I'll warn you, the notes for this chapter are extra wordy. Okay, and the reason for that is I know functions of multiple variables are strange to most students. So I tried to put in a lot of information. So I'm not going to read the notes to you, but we'll hit the highlights as usual. I'm going to begin by sharing my browser and show you where we are in the course. Okay, we are currently in week 14. Okay, so there's one more instruction week after this, and then the final exam week. Okay, so again, just a quick scroll down to show you what's coming. Assignments this week are due on May 9th, Sunday. And we're going to first start with functions of multiple variables and then partial derivatives. They're called partial because you have a choice as to the variable you're differentiating with respect to. Okay, and you kind of, we'll talk about what those derivatives mean graphically and other things. Okay, one thing I want to share with you is your TI-84 will be pretty useless for this chapter, except for evaluating functions of multiple variables. That we can do on a TI-84. You can't graph these on a TI-84. Okay, can't graph them because you're missing a dimension. Okay, your TI-84 is only going to graph a function that has one input, one output, because you can graph that on a flat surface like a TI-84 screen. Okay, these functions, if you have two inputs and one output, well, they're harder to graph. And then functions with more than two inputs, you really can't graph them at all. Okay, so I'll show you some tools that I've included in the course, like this Wolfram Alpha 3D plotter, okay, that will help you when you've got functions with two inputs and one output, okay? And you might be able to graph them. Please note, this is a really basic free calculator. So as such, it's, well, basic. It doesn't let you rotate the image. It doesn't let you zoom in. It just kind of plots it. So I'll show you how to interpret those as we go along. For assignments this week, we've got 2 homeworks and another discussion board. Okay, and all that's due by May 9th. Okay, here's week 15, the last week of the course. It's an instructional week. And then here is our final exam. Okay, so that's kind of all that we got coming up, folks. We're getting very close to the end. So if you have anything you need to complete, okay, please try to do it within the next 2 weeks. Okay, so I'm going to begin by opening up the functions of multiple variable notes right here. Okay, and so give me a moment to share those with you. Oops. All right, now share the content. All right, so everybody should be seeing my notes. Section 4.1, functions of 2 or more variables. Okay, now I'm going to spend some time reviewing function notation because that's critical in order to understand what these functions are telling you. Okay, you're usually used to a function of one variable looking like this. We sometimes will call the output variable y and say y equals f of x. Okay, and that tells you that you've only got one input, right? Remember, this is your input and y is your output. Okay, I find that this is the thing that confuses students the most. What goes into the function, what comes out of the function. So if I extend this to a function of two input variables, I can write it like this, f of x comma y. This tells you these are both inputs. All right, and my output here is a z, okay? Or f of xy, okay? So again, your inputs are called your independent variables, okay? Because there's things you can either control or things that tick along by themselves like time, okay? And your output variable depends on those values. Once you pick values for your inputs, your output is determined, okay? Now, again, this function f is going to associate one output value z for each pair of inputs x and y. Okay, so the x and y together will determine a value of z. Okay, and I alluded to this in my introduction. An example of a function in economics is called a Cobb-Douglas production function. Okay, so how do these work? A company's production of a good or a service is actually related to two inputs, its capital investment and the size of its labor force. Okay, and that's probably an oversimplification, but these are used a lot in economics, okay, and modeling in general. And I'll show you how they work. Okay, we'll talk about them in a moment. So rather than get into specific examples of Cobb-Douglas production functions or any other type of function, what I want to get you comfortable with is ways these things can be represented. Okay, you're used to a function like this, y equals f of x, as being a curve on a two-dimensional surface like a whiteboard, right? Or a calculator screen. Right? Everybody knows what I mean by a two-dimensional surface, right? Like a whiteboard or a calculator screen. It's flat. It only has a length or a width. So one way you can represent a function of two variables is with three dimensions. You need one more dimension. What's the extra dimension for? Is for the output value. Just like here, okay, if I have just one input value, well, those can be represented on a single line, right? But I need the second dimension to handle y up here, right? So I can put my x values along an x-axis, but as soon as I introduce a y associated with each one of those x's, I need a second dimension, an up-down, okay? Just like that, when I have functions of two variables, x and y, you can think of the xy plane being just like I have on this diagram, being on the floor. Okay, see x and y here? And the z value is a third axis that's kind of like the edge of where two walls meet in the room. Okay, so think of x and y as being the length and the width of the floor in your room, and think of z being height above the floor. Okay, does that image work for everyone? Okay, so I'm asking you a question. Does that image work for you of this being like the length and width of the floor in your room and the z-axis being, well, like a corner of your room, and so z is going to be the height off the floor? Okay, so could you please give me some feedback? Does that work for you? Yes? No? I'm not hearing anything or seeing anything. Okay, I got one yes. Anybody else? Does this image of three dimensions in space work for you? Okay, another yes. How about the rest of you? We have 13 of you on. Okay, good. All right. Thanks for the response, everybody. I appreciate the feedback because it lets me know whether I need to keep explaining or whether I can move on. Okay. All right, so here's kind of a picture. Okay, so now what you have to realize is rather than an ordered pair on a whiteboard, okay, now what we have are called ordered triples, X, Y, and Z. And they would identify a point in space, right? So I can pick any ordered pair on the floor, and then a point in space above it would be the Z coordinate. Okay, just like this diagram here. Okay, so pairs of axes, like here's the XY plane on the floor. Okay, point Q here is on the XY plane. It has an X value and a Y value that aren't zero because it's somewhere in this plane. But notice its Z value, the last coordinate in the triple, is zero. Why is that? It's sitting on the floor. It's not floating in space. Okay. Likewise, if I have the XZ plane, which is one of my walls, it has a Y coordinate that's zero because again, it's pretty much on the XZ plane and it hasn't moved left or right off of that plane. Same thing with the back wall over here. This is the YZ plane and you can see its X coordinate is zero. Okay. So you're used to saying things like, well, if I'm on the x-axis, my y-coordinate is zero. If I'm on the y-axis, my x-coordinate is zero. Well, now you have to worry about three planes, xy, xz, and yz, okay? And like the two-dimensional analog, okay, whichever variable you're not moving, okay, that value is going to be zero. Okay, and you can see this point P that's floating out here in three-dimensional space. It's got an X coordinate. Okay, that's telling you how far from the origin you are. And the origin's the corner of the room over here. And its address is 0, 0, 0. The origin. Okay, so this point P is X units forward from the origin. It's Y units to the right of the origin, and then it's Z units up in space. Okay? So what you can do with these functions is you can evaluate them just like you can a function in two variables, where if somebody gives you the values of the inputs, right, and they say, hey, X is 2, Y is 3, find the value of this function, Z, right, when you've got certain X values. Okay, so you can evaluate a function just like this. All right, so here's my example. I've got Z is G of XY, and just like in the two-dimensional case, it doesn't always have to be F, right? I could call the function anything that makes sense. Okay, and here I have two inputs, and they're telling me evaluate this when X is -1 and when Y is 2. So all you do is the same thing you do in the two-dimensional case. You're going to plug in -1 for the X, and you're going to plug in 2 for the Y. Okay, so you can see that everywhere that I have an X, there's now a -1, and everywhere there's a Y, there's a +2. This is probably the only thing you can kind of do on your TI-84, which I'm going to share with you right now, if you've got that, okay? Or you can do it on the Web 2.0 calculator that I've included in our course. Okay, all you need to do in order to do this is just type it in the way it's written. Okay, so I have -1 squared minus 9 times -1 times 2. That's the -9xy plus 2 squared. Okay, please remember, I don't need to put the 2's in parentheses, but the -1 for sure has to be in parentheses if I'm going to raise it to a power, okay? Remember to do that. So as a matter of choice, I just put all of my variables in parentheses, then I don't have to think about it. So you can see the value that I got from evaluating this is 23. Okay, and that says Z is 23 when when x is -1 and y is 2. So I can write this as a triple. Okay, so this is the analog of an ordered pair. I can say here's -1, here's 2, here's 23, and these refer to x, y, and z. And yes, they're in order in an ordered triple, just like they are in an ordered pair. Okay, anybody have questions on evaluating these kinds of functions? Okay, anybody? Questions on evaluating them? It's just a matter of understand what the input means. That's x, that's y. Okay, because again, it's written that way. Okay, so just pull the values out and plug them into their respective variables. Okay, and what does this mean graphically? Okay, functions of two variables I can represent with something physical that you can imagine. And think of it like this. G of xy is a surface that's floating over the floor. Okay, the z values are points on the surface, right? And the xy values are points on the floor underneath each of the z values, right? So this surface might look like a mountain range. It might look like peaks and valleys, okay? And what I have in the course, again, I can't graph it on here because I don't have enough variables. My calculator can only handle functions of one variable. So what I need to use is an actual three-dimensional plotter, okay? The one that I have in the course is called the Wolfram Alpha, a 3D plotter, and I have it open in my browser. So what I'm going to try to do is graph this function for you just to show you how it works. Okay, graph this in the Wolfram 3D plotter. Okay, so I just want to show you what they look like. And again, you're looking at it on a two-dimensional screen. So what it is like an artist's rendering of what a three-dimensional surface would look like. Okay, you're used to looking at pictures of mountains and valleys. So I think you'll be able to handle what this gives you. Okay, I have 3D plot open. Okay, and let's see if I can type this in without messing it up. It uses calculator notation. So I have x squared, and I'm using the caret, minus 9xy plus y squared. Okay, everybody see the way I entered that? Yeah, it's kind of like matrices, yes. And it's a use calculator notation to type in the function. Okay, so you need the caret to raise to a power. All right, and then I'm going to hit equal and see what it does. Okay, and then we'll talk about the graph. Okay, it names it. It's a hyperbolic paraboloid, and this is part of the graph. Okay, and again, what is unfortunate about the way it does this, okay, what you're looking at is kind of like the middle of a saddle. Okay, think of it like we're facing the front of the horse. Okay, so the saddle goes up in the front and up in the back. Okay, and then it dips down on the sides where our legs are. Okay, so this is what's called a saddle surface. Okay, we have a low point over here on the right side and a low point on the left side where our legs would go over the saddle. Okay, and you can tell, oh, in these shaded diagrams, it's going to graph it like a grid, and it's going to kind of make the lower z values darker. Okay, so lower z values, let me type what I'm trying to say, are darker. Okay, so here's a low z value, here's a low z value. But again, because this is my free version, okay, and Wolfram really wants us to pay for a premium version, I can't rotate it, I can't extend the axes boundaries or anything else, okay? One helpful thing it gives you is this thing called a contour plot, okay? And here you can kind of see the shape of the saddle. Here are the sides that drop off where our legs would go, the dark pieces. And the lighter pieces, you can see Here's showing you the Z values are going up as we go in this direction because the diagram's getting lighter, okay? So darker values are smaller Z values, lighter colors are higher Z values, okay? This is called a contour plot, okay? You can think of it like a two-dimensional projection of this surface, okay? So again, that is the best we've got as far as graphing. And remember, it only works with 2 inputs. If I have 3 inputs, I can't even do this, okay? That's the best we've got with graphing. And you can kind of see, all right, well, here's a high point, that's a low point, that's a low point, here's a high point. Okay, I'm good with that. Okay, you kind of just want to know where they are. Right? Questions on 3D plot. We'll use it again. Okay, I just want to see everybody okay with this. The link to this is in the course. It's in week 14, and it's in the online tools and calculators module. Okay, and again, this is just so you're not completely, wandering around. Anybody questions on it? Okay. Well, I'll go back to the examples. Right? Just like functions of one variable, functions of multiple variables also have domains and ranges. Okay, so what's the domain? Well, domain has the same definition. It's the set of input values that give you a valid or a defined output value. Remember when we worried about domains of functions with one input? We said, well, we have to exclude any X values that make the output undefined, right? And those could be things in a rational function that make your denominator 0, things in a square root function that make the value under the root sign negative, okay? So you have similar domain considerations with functions of more than one variable, but they're a little extended. Okay, the domain is going to be the set of ordered pairs X and Y, because they go together, that for which the output is defined. Okay, so for example, say we have this function, g of xy. Okay, you can tell it looks sort of like a rational function, except it's got 2 input variables. And you can tell from looking at the denominator, if x equals y, the denominator is 0. Okay, and just like any function rule, we couldn't allow this denominator to be 0 because that would make the output value, g of xy, undefined. I'm not allowed to divide by 0. Okay, that's an undefined thing to do. Okay, so you can state the domain of the function as a set of all ordered pairs xy such that x does not equal y. Okay, if you want to write it in set notation, you can write it like this: set of all ordered pairs xy such that x is not equal. Okay, so there's a domain statement for a function with 2 inputs. Instead of just an x here, we have an x and a y, and here's a condition on x, y, or both of them. Okay, everybody okay with the definition of domain? Everybody good with this? Okay, so again, it's exactly like what you're used to. It's just now you've got to worry about y as well as x. Okay. Now we're going to assume that none of the functions we're dealing with in this course are weird. Okay, what do I mean by weird? I mean they don't have discontinuities. Okay, think of the surfaces that we're going to build are all going to be nice, smooth, rolling hills and smooth valleys. No cliffs, no breaks, no black holes, nothing weird. Okay, so no discontinuities. Okay, so do those functions exist? Yes, of course they do, but they're used to model much more complicated situations than what we're going to be talking about. Okay, So here's one for you to try, okay? See if you can find the domain of the function f of x, y. Okay, so I'm asking you to do this one. Okay, find the domain of f of x, y. Type done when you're finished. Okay, so that's the one right here in the middle of the page. Okay, see if you can find the domain. And don't worry if you have to say it in words. Don't worry about writing it as set notation. Okay, don't forget to consider what can happen if x and y are negative. Okay, we'll take another minute or so for this. Those of you who are posting in the chat are on the right track. Okay, yeah, you have to consider the fact that the further away a number gets from zero in either direction is going to matter. Okay, so consider the negative numbers as well. Okay, we'll take another few minutes. Okay, well, I know not everybody's finished, not everybody posted something, and that's fine. I want to just make sure we're all on the same page with this. Okay, what do I have here? I have a difference of two squared things in my denominator. So I have to worry about this difference giving me a 0, okay? And then I have a square root. And I know I can't take square roots of negative things. All right, it's all right to take square root of 0, except for the fact this square root's in a denominator. So I would have been okay with people saying the denominator can't be 0, and the square root can't. Actually, let me say it in a more reasonable way. Okay, the quantity under the square root, under the radical, can't be 0 because it's in a denominator, or negative, right? So it can't be 0 because it's in the denominator of a fraction, and it can't be negative because I'm taking a square root. If I take the square root of a negative number, I wind up in imaginary numbers. I don't want to be there. Okay, f of x, y is supposed to be a real number. Okay, so how do I handle that? Well, I could say x squared minus y squared has to be greater than 0. Notice I didn't put an equal there. Okay, if this were not in a denominator, I could put an equal sign here. Okay, then I get that x squared has to be greater than y squared. Okay, and you realize if I take the square root, that gives me a plus minus. Okay, so as I think it was Tuyen said in the chat, what you want is the absolute value of x being greater than the absolute value of y. All right, why is it not okay to just say x has to be greater than y? Well, if you think about the situation, okay, if x is negative 10 and y is negative 5, okay, x is not greater than y. But if I take the absolute value, if I square them, then I'm going to get 100 minus 25 under here, and that's perfectly okay. All right. So again, you're thinking about how far away is this from 0, okay, because once I square it, I'll get a positive number. So think of it this way. Squaring and absolute valuing are the same way to get positive numbers under here. Okay. So everybody okay with this example? Anybody have questions about why it works? Because again, remember, the further left you go on the number line, right, the smaller the number. Okay, so negative 10 is smaller than negative 5. Okay, just think about what you want in your bank account. I'd rather have negative 5 than negative 10. Okay. All right, good. All right, I'm not seeing any comments, and I realize it's tedious to comment all the time, but if I don't see anything, I'll just keep going, okay? Please stop me if you've got questions. So let's talk about how to apply this. All right, so here I have a cost function, okay? And this is a furniture company's cost in dollars to manufacture 1 unit of a cabinet, where X is board feet of lumber and Y is work hours of labor required for assembling and finishing. Okay, so let's say a particular one of these cabinets requires 10 board feet of lumber and 3 hours of labor to make. That's like saying evaluate C of 10, 3. So again, all you have to do is keep track in an applied problem of what the variables represent. Okay, so here the X is the board feet of lumber and the Y is the labor hours. Okay, and if I plug them into this cost function, I'm going to get a cost in dollars. So $665 to manufacture the cabinet. Okay, so again, this is just a function relating two input values that are used to manufacture the cabinet to an output value like its cost. Okay, now again, these are represented by surfaces in three-dimensional space. Okay, so if you set up your X and Y value table properly, Excel can graph these sort of kind of. Okay, again, Appendix D refers to something in a different course. Okay, if anybody is really into using Excel to try to graph, let me know. I think Wolfram Alpha is okay for most of our purposes. Okay, Wolfram Alpha is okay. But if you're really interested in Excel, let me know. Okay, and I will. Okay, I will let you know. Again, I apologize for not updating these notes. They were connected to a slightly different text. Okay, but we will cover all this stuff. Okay, so here's what this function, okay, our cost function looks like when it's graphed by Excel. Okay, you can see it has a high point over here. Okay, and again, you can think of this as the XY plane down here. And Excel is trying to render this as the Z axis. Personally, I think Wolfram Alpha is a little easier to look at than this. Okay. But again, my personal favorite for graphing these is a program that's used in engineering called MATLAB, and I'm trying to get a license for that. Okay. It's an expensive program, and all of the licenses we have at South go to the engineering department. So till I can get that, we're kind of stuck with what we can get for free. Right. All right, another use of these functions of multiple variables, and again, these are all going to be examples with two inputs, but please realize that it's possible to have more than one, okay? Kind of like matrices, I think Zainab mentioned that, okay? So here's another example, and this one also comes from economics. It's called utility functions, okay? And they're measures of the satisfaction a consumer gets from the consumption of multiple goods. Okay, now what can that be? Well, it could be two things that go together. The classic example that's used in most econ books that I've seen is cornflakes and milk, for those of you who eat cereal. Okay, cornflakes are not as fun unless I have milk to put on them, and I don't drink milk unless it's on my cereal. Okay, so basically that's kind of a utility where the two goods have to go together. Okay, you can probably think of other things like maybe your phone and your earbuds. Okay, things like that. Okay, so that's the general idea. Okay, so the graph of all points with the same utility to the consumer is called an indifference curve. And these are these curves labeled U1, U2, and U3. Okay, and again, let's say you have a utility function for two goods, X and Y, like cornflakes and milk. And let's say it's given by U equals X squared, Y squared. Okay. And so the consumer purchased 8 units of X and 2 units of Y. Okay, so whatever that is, it could be in ounces, right? 8 ounces of cornflakes and 2 ounces of milk or whatever. The level of utility for these two purchases would be 8 squared times 2 squared, or 256. Okay, so if you wanted to be on the same utility curve, and instead the customer purchased only 4 units of X, right? That would be 16. How many units of Y would they need to purchase to get the same utility? Okay. So let me show you that. Okay. You can see what would that look like. I'm going to work it here so you can see what it is. So only 4 units of X instead of 8. And then I want to know Y squared. How many units do I need to purchase of that to have the same utility to meet? Okay. So how would you do that? Well, 256 is the utility I'm interested in. 4 squared is 16. Okay, so then I'm going to basically divide both sides by 16. Okay, it turns out 256 is a perfect square. Okay, and it's 16 squared. Okay, and then the only thing I need to do is take the square root of both sides. Okay, I'm just solving the equation. And I'm going to take the positive square root because we're talking about goods, right? And it doesn't make sense to have negative numbers of goods, right? I said these could be ounces of products that have to work together. So I would need 4 units of Y, right? I'd have to up the amount of Y I purchased or consumed to have the same utility if the amount of X went down, okay? And essentially, you can see that would leave me along the same utility curve. Okay, so all of these are different utility curves, right? And again, this one would be, say, defined by 256 as the utility. This might be a different value of utility. Okay, and I guess economists use these to make predictions about, well, if the consumption of this good goes down, what's going to happen to the consumption of the related good? Okay, how much will that change? Okay, and again, here you can see is the worked out math for what I just did. Okay, and what you can do is you can find a specific utility curve, like say you're interested in the utility curve with a U value of 256. Okay, all you have to do is solve that for y, okay, and take the positive square root, and then you can just plug in x values and solve for y, right? Plug. And solve for y. And that'll give you XY pairs that have the same utility. This can even be simplified to give me 16 over X equals Y. Okay, which is exactly what I did, okay, when I solved it before. Everybody understand the concept of a utility curve? Okay, I'm asking a very broad question here, okay? Everybody understand the concept that there are two goods who are related? Consumption of one increases, consumption of the other will go down, and vice versa. Okay, so they're related by those curves. Right, so again, I'm just trying to show you examples of functions that have two inputs. Okay, so are we good with utility? Yes, no, maybe? Okay, good. All right. But let's get to the more interesting one, and that's the Cobb-Douglas production functions. Let's take a look at those. Okay, and again, these are all things you would see in an economics class. I'm trying to think, probably a macroeconomics class. I'm not really sure where they cover it these days. Okay, so here's the general form of a Cobb-Douglas production function, right? The Q is our total value of our production, the real value of the goods produced in a time period. So this is our output. Okay, and then we have two inputs. We have labor and capital, and they're using a K for capital. These are input variables. Okay, L and K are the inputs, and notice they're raised to powers. Okay, they're basically they're using Greek exponents, alpha and beta, okay? And they're called elasticities of capital and labor, okay? So basically elasticity is the idea of how much your variable is going to change if you move stuff around. In other words, how elastic is it? Does it move a lot or does it stay fixed? Okay, so these exponents are the elasticity for capital and labor, okay? And these are usually something you can determine with technology, okay? Realize this is a model. This function is a model that's built from data, okay? Model built from available data, okay? So again, the examples we're using in our text are fairly simplistic, okay, because again, we're trying to show you how they work. But if you were using a real one, you know, these coefficients and exponents might be messy, okay, because they come from real data. Okay, so L is your labor in like labor hours in the same time period as your production. And capital is the real value of all of your machinery and equipment and things. And A is a coefficient, okay? It's a coefficient that's not dependent on your inputs, right? It's a factor that influences productivity, like maybe it's an era of rapid technological change, right? Like, for example, cars are going through a period of rapid technological change with a lot of the self-driving technology. And particularly for electric vehicles, a lot of improved battery technology. So that would be the type of thing that would influence this A coefficient, okay? And again, gathering this data and interpreting it to build the function is by no means something that's straightforward or easy to do, okay? So all we're doing is trying to see, okay, what will this tell us once we actually have the model, okay? So again, let's talk about the exponents, alpha and beta, okay? And again, I'm trying not to turn it into an economics class, but I just want to explain enough of it that this makes sense to you. Otherwise, it's just another dumb math book problem. And these can be pretty powerful models. Okay, so if alpha and beta both add to 1, all right, like let's say alpha is 1/4 and beta is 3/4, the production function has what's called constant returns to scale. So what that means, if you double the capital and labor, you'll double your output. Okay, if alpha and beta are less than 1, the returns to scale are decreasing. Okay, so you won't recoup back what you put in. And if they're greater than 1, the returns to scale are even better. Okay, so basically what we are going to assume for most of these examples that alpha plus beta is 1. Okay, and again, we can think of them as capital and labor shares of your production. Okay, your output. Okay, so we're assuming an ideal world, ideal conditions. Okay, so hopefully that wasn't too complicated. All right, so does that make sense? Okay, again, I just want to make sure these production functions sort of make sense. Okay, and they're a little weird looking. Again, notice we don't have an X and a Y and a Z, but that's okay. Okay, they mean the same thing. We're calling K and L, okay, capital and labor. You could call it, okay, P of XY, where X is capital and Y is labor. There's no reason why you couldn't write it like that, okay, as long as you understand that in my example, K and L are inputs. In another example, they might be X and Y. Okay, so it's important to be really, really solid with the function notation. Okay, so you're sure what's input and what's output. So let's look at an example. Here I am. Okay, suppose a company has this Cobb-Douglas production function. You can see here's my capital, here's my labor, and you can see my alpha and beta, my two exponents will add up to 1. Okay. And then they tell me what the units are for each of the variables. The output variable is in thousands of dollars in weekly production value. K is hundreds of dollars of capital investment per week, and L is work hours of labor per week. Okay, in applied problems, please pay attention to the units. Okay, the reason for that is sometimes, like this problem here, your units are scaled, right? So if Q comes out being 45, that doesn't mean $45 or 45, what it means $45,000. Okay, so you need to make sure that not only do you scale the outputs, but you're scaling the inputs. If you want to invest $6,000, you're not going to plug in 6,000 for capital because that's in hundreds. Okay, you're going to basically plug in 60 because 60 hundreds is 6,000. Okay, so understand the scaling. Understand the scaling idea. Okay, we've seen this before in other applied problems, and I can tell that some folks really, really don't like it. Okay, but it's a fact of life with these types of business models. Okay, things are scaled. Okay, so if my current capital investment, okay, this is K, okay, is 64,800 a week, okay, and work hours are 4,064 hours per week. Okay, well, I'm looking at labor hours as work hours per week, so I'm okay with the L value. But I obviously need to scale K. Okay, and the way I do it is I'm going to take 64,800 and I'm going to divide it by 100. I want to see how many hundreds of dollars are there in 64,800. Okay, and that'll give me 648. Okay, that is the K value I need to plug into the production function. Okay, and then I just evaluate Q, and you can do this with any sort of scientific calculator. I'll bring up my TI and show you how that works. Okay, I would say 4 parentheses 648 raised to the, and then just type in 0.35, step out of the exponent, parentheses 4064, raised to the 0.65. Okay, and again, this would work also on the Web 2.0 calculator. You just use y to the x, or I forget if it's y to the x or x to the y. Okay, but you use that to create the exponent. Okay, so I get 8549. Okay, but this is in thousands of dollars, right? Let me just close this. Okay, it's in thousands. So weekly production value, I'm going to multiply this by 1,000. Okay, and that gives me $8,549,000. Okay, so usually, to get a hang of this, when you're putting values into a function with scaled variables, you're going to divide. Okay, when you take values out of a function, if your output value is scaled, you're going to multiply. Okay, everybody see how that works? All right, so again, I just want to make sure the thing to understand here is how the scaling works. Okay, so let's say we want to change things. Okay, weekly capital investment is increased to 72,900. Okay, I'm going to divide that by 100. So now K is 729. And I'm going to hire extra contractors. So I'm going to increase my labor hours to 5120. Remember, K was 729. Okay, find the percent increase in production. Okay, so the first thing we need to do is first find Q. Okay, so I'm finding my new Q value. And again, I'm not scaling it, okay, because I'm going to use my other unscaled value. Okay, so here's my increased, my new Q value. Okay, and it's still scaled. Okay, so they asked me to find percent increase. How do you do that? First, find the difference. Right, so I'm taking my new value, 103.52, subtract the old value of Q. That gives me a difference of 1803. Then divide by original value. Let's say old value. Okay, which was 8549, and then multiply by 100%. Okay, this is how you find a percent difference. Okay, it's got these 3 steps. So you can see, here's my difference. I'm dividing it by the original value of Q and then multiplying that by 100. How would that look on a calculator? It would look like this. I'm going to use my fraction template. So I have 1803. Sorry. Divided by, whoops, sorry, 8549. Right, so there's my fraction. And then I'm just going to multiply that by 100 and slap a percent sign on it. Okay, I don't have a business calculator here with percents, so I'm just going to say multiply by 100. I want it as a decimal, so math, defs, and I get 21.09. Okay, so approximately 21% if I round it to the nearest whole percent. So that gives me a 21% increase in production. Again, I might want to play with those values, okay, my production values, if I were a business person. Okay, if I change this by how much, what do I have to, what production change would I get? Okay. Here are some practice problems. Okay, and again, I'll show you these different categories. My main idea right now is to show you various types of functions of a these are called multivariate functions. Okay, by multivariate, it means they have more than one input variable. Okay, so far we've looked at Cobb-Douglas production functions, utility functions. This is a compounding function. Okay, so for example, if you want to see how to calculate a payment, okay, on a basically a loan that's what's called amortized, where namely like a car loan or a mortgage, where each payment is the same amount, but each payment has a different amount of principal that you're paying off and interest. And in amortized loans, you pay the bulk of the interest up front or early in the loan, and the bulk of the principal later in the loan. Okay, so here's a payment formula for that type of a loan. And you can see it's a function of I and N, okay, where I is your interest rate as a percent, and N is the number of years before the mortgage is paid off. Okay, so say maybe a 30-year mortgage. So here we're saying, okay, our interest rate is 7.5%, and the mortgage has 20 years to go. Okay, so basically, this is the mortgage amount. Okay, so this is the amount you're borrowing. Okay, and the other things in here, like this 0.01 just turns the 7.5 into a decimal, 0.075. The 12 is your amortization period. Okay, if you're making monthly payments on a loan, like a car loan or a mortgage, every month, okay, the interest kind of compounds. Okay, so basically that's what the 12 is for. Okay, and if I wanted to do this on my calculator, okay, this is a bit of a gnarly formula, so I'm going to use my TI. I'll show you how to do that. Okay, so I'm going to clear this. And I'm going to start out by saying 100,000. All right, and I'm going to multiply that by this, and I'm going to use my fraction template for this. So alpha y equals numerator over denominator. And I have 0.01, okay, and then parentheses, and my I is divided by 12. I can use another fraction template here, alpha y equals. Okay, my interest rate, they said, was 7.5. Okay, and that's going to be divided by 12 because I'm making monthly payments. So there's my numerator. Okay, my denominator is 1 minus parentheses 1 plus the same 0.01. Okay, and the same fraction. So alpha y equals 7.5 over 12. Okay, so this closes the parentheses on the fraction. This closes the parentheses out here. Then this has an exponent of negative 12 times 20, where 20 is the number of years on the mortgage. So I'm going to say negative sign 12 times 20. Okay, so everybody see how it gets typed in? See how to type it in? Anybody questions? Anybody having a question? Somebody unmuted. Do you want to ask something? Okay, so the TI is real easy using that alpha y equals numerator over denominator. If you're using the Web 2.0 calculator, you just need to look above the calculator to make sure it matches the structure of the formula. Okay, so here's how I did it on my TI. And I got 805.59. Okay, and I'm basically going to write it like dollars and cents, because remember, it's a payment amount, a monthly payment amount. Okay, and what that means, the interpretation of it is when the interest rate is 7.5%, and the term, okay, the end value is called the term, is 20 years. The monthly payment is 805.59. Right? And this is an example of, say, if you borrowed $100,000 to buy a house, right? Maybe you put down $20,000 as a down payment, so the seller would take the house off the market for you, okay? And then you went and got financing from a lender for the extra $100,000. Say you don't have that much cash sitting around, okay? This is what you would have to pay your lender every month to pay off the loan, and it would take you 20 years. Okay. Everybody okay with that example? One example, everybody good with that? Anybody questions on the loan example? Okay, so those are pretty much a smattering of business type examples of multivariate functions. There are lots of these functions in physics and engineering. Lots of these functions in okay, so I'll just show you a few of them. We won't worry about the details. Okay, so one of them is something called the universal gas laws. You might have heard this in either a physics or a chemistry class. Okay, and again, the idea is that you can take a gas like hydrogen and you can compress it really, really tightly, or you can let it expand and it will fill a large space. Okay, so this is again called the universal gas law, and it applies to not just hydrogen, but other gases as well. And the idea is pretty much the more you compress it, the more pressure you put on the gas, the less volume it's going to fill, right? That's how they fill those gas cylinders you might have seen for, say, welding, right? Like oxyacetylene torches or things like that. They compress the gas to fit it in a cylinder. So those things are related. And also, the more you compress a gas, the hotter it gets. Okay. So the variables in here are volume is a function of temperature, T, and pressure, P. Okay. So those are the three quantities that are related by the universal gas laws. And we can solve this equation so any of these variables is an output value. But right now, this is solved with volume as the output, temperature and pressure as inputs, and R is a universal gas constant. It's just a constant that chemists and physicists have found out makes the equation work. Okay, so don't worry about its units. Okay. And then again, we have a number N that tells you the amount of gas. Don't worry about what it's measured in. Okay, it's a chemistry unit. V is volume in milliliters. Okay, pressure is in atmospheres, right? And temperature is in a unit called Kelvin. Okay, so I'm just going to show you how to plug in the values. So here's my universal gas law expression. Okay, and then all I need to do if I want to find the volume, okay, and again, volume is going to be in milliliters, I plug in my numbers, okay, and I'm not going to worry about the units. 12 is my N value. Okay, R is that universal gas constant that they said not to worry about the units. Okay, and then T is 50 Kelvin. And pressure is 2 atmospheres. Okay, so I'm just plugging in the given values. And then this is something that you would be able to do on a calculator. Again, this first unit in this chapter, this first section in this unit is pretty much the only ones where we'll actually be able to evaluate things on a calculator, right? So I can do the same thing, alpha y equals, and then put my values 12 times 0.082054 times 50, the whole thing. Oops, that should be a times, not a divide. And then the whole thing divided by 2. Okay, and I get 24.6. Okay, so 24.6, and they said this was in milliliters. Okay, so again, simple evaluation. Simple formula evaluation. Okay, and again, I'm sure some of you have taken science classes and you've done problems like this. All right, so here's an indifference curve. Remember, we talked about that. We talked about utility curves. Let's say we have an indifference curve with this equation, xy equals 500. This is my output value. Okay, if 25 units of X are purchased, how many units of Y must be purchased? So what is that telling me? It's telling me solve for Y. They've given me a given output value, a given utility value of 500. And now they're just asking me to find points that are on that same indifference curve. Okay, so I'm going to take xy equals 500. And I'm going to divide both sides by x. So that gives me y equals 500 over x. And all I need to do is plug in my given x value, which is 25. Okay, and you can see that'll give me 20 units of y. Okay, and it says graph the indifference curve in part A to confirm your result. Well, an indifference curve, since 500 is plugged in for you, I can graph this on my TI, right? All right, since the 500 is plugged in for this, I can graph this on a TI. Okay, and essentially the way I would do it is I'd graph this, y equals 500 divided by x. Whoops, sorry, wrong button. Here's 500 divided by x. I'm going to go in here and I say 500 divide by x and make sure I'm on a standard window. And again, that's not going to show me much, right? But let's just take a look at what it looks like. Okay, and you might say, hey, where's the curve? Okay, so again, you can see your values of x or y are 20 and 25. This is only going to show you from 0 to 10, right? So you might have to change your window. I only want to see positive values, so I'll make my x min 0. I'll make my x max 50, and I'll do the same thing for my y. I'll go from 0 to 50, right? Because you know here that 25 and 20 are an ordered pair on the indifference curve, right? So I'd have to see that. And there's your indifference curve. Okay, and you can even get on it and find this ordered pair. So I could do second trace calc and ask for value and say when x is 25, what's y? And it'll give you the 20. Okay, so see how to graph. And you're basically graphing a specific indifference curve. Got to graph a specific one. Okay, as long as you have a value for the output, this can be graphed in 2 dimensions. Okay. Anybody questions on it? Okay, the last example we'll do is a Cobb-Douglas one. And again, you can see here my alpha and beta sum to 1. Okay. So a company's units of production, here's our output, are given by this Cobb-Douglas production function where K is capital and L is labor. Here are my inputs. Okay, and again, these, they're not saying anything is scaled. Okay, so in this problem, nothing is scaled. Okay, so no scaled inputs and outputs, or they would have said, you know, K is dollars and hundreds. They said dollars of capital investment. Okay. So again, I want to see what I've got here. So it says find Q if K is 64,000 and L is 512. So I have Q equals 70 times 64,000 squared. And this is 512. Nope, not squared. It's 2/3 up there. And this is 1/3. Okay, so on your TI or other calculator, that's again pretty straightforward. Let me get out of here. It's just an evaluation problem. It's 70 times 64,000. And then you just do a division up here in your exponent. So 2 divided by 3. There's your exponent. Step out of there. And then the other piece is 512. Raise to the, and do the divide again, 1 divided by 3. Okay, realize these are, this is a cube root, and this is a cube root of something squared. Okay, these are called power functions. Okay, and these give you a value of 896, right? 1,000, and that could be the value, okay, of your production. All right, now remember we said back at the beginning, if alpha and beta are exponents equal 1, okay, we have constant returns to scale. So what we want to do is we want to halve K and L. So I'm going to take K is 64,000 divided by 2. That's 32,000. And then 512 divided by 2. I believe that's 256. Yep. And then I want to show that I get half of my Q value. All right, so Q is 70 times 64, 32,000, sorry. $256 to the 1/3. Right, and I'm expecting to get half this number, okay, which I'll just figure out what that is really quickly, 448,000, okay? So I'm going to go back to my production function, and I'm just going to go and retype my new values. Okay, so I just did second entry, and now I'm just going to change this to 32, and change this to 256, and hit enter. And you can see it works. Okay, so yes, I do get 448,000, which works. Okay. Again, if you hold capital investment at 64,000, graph Q as a function of L. Remember, if I hold any of the variables constant, I can graph in 2 dimensions. Okay, does everybody understand why that's working? Okay, so I can graph in 2 dimensions. So what they're telling me to do, okay, is to basically hold this constant, right? So basically I can say L is basically the function variable. Okay, so this would become okay, that would be my function. Okay, now on my TI, this is going to be Y1, this is going to be X. Okay, so I'm going to go into Y equals, clear that out. And I'm going to have 70 times 64,000 to the 2/3. Okay, and all that's just a constant, right? No variables yet. And then I have my L, but I'm going to call it X to the 1/3. All right, and let's try graphing that. Oh, I have my old things from last time. Okay, hold on. Okay, might be easier to do this on Desmos, or I have to play with my window to try to see what I'm getting. Because again, I have a large constant here, even though I'm taking a cube root. Okay, so again, I can play with my windows to see what I can see here. Personally, I prefer to just do it on Desmos. So I'm going to just go over there briefly and show you that. Okay, and again, my output will be Y equals, and I just have the same constants, right? So 64,000 raised to the, and I believe here I need the parentheses on my exponent. Maybe not. Okay, because I can step out of my exponent. And this was, I'll say X instead of L, and raise that to the 1/3. Okay, so you don't need the parentheses. And again, to actually see it, you probably have to zoom in a little. And play with the graph. Again, part of the problem is my scale is so huge. I'm probably going to have to just change my scaling. It's not letting me do that. Oh, my chat's in the way, sorry. Okay, so let's make these from 0 to, my values were about 448,000, right? So how about 500,000? And 0. And again, I'm still not seeing much. Okay, so I'm probably not doing something quite right here. Okay. But again, you can see the general idea. Here is your X, your input value, and you're just holding your K constant. Okay, so I need to figure out why Desmos is not reacting the way I want. Ah, there it goes. Way, way, way out. Oh my, look at that. Okay, way out into the millions. I said it has to look like a cube root because that's what this function is. So it's not till you get up to Y is 5 million that you actually see anything. Okay, so easier on Desmos. Scale the graph. Okay, so again, I definitely encourage you to use Desmos. Okay. So at this point, do we have questions on any of the examples? Any of the examples? You can see all we did was evaluate, 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 evaluate. And the only thing we had to pay attention to is what are the input variables? What's the output variable? So again, I'm asking you for feedback. Any questions on the examples? No, not seeing any. Okay, so questions in general? Questions in general? Anybody have questions?